Hello, my name is Lars Bogaerts, and I will be the presenter of our recent findings. The title of our work is Numerical Optimization of the Lifetime of Plastic Injection Molds Produced via Additive Manufacturing. This work can be approached from two perspectives. First, with the introduction of modern standards, demands, and computer-aided engineering, product shapes are becoming increasingly complicated, which is an open goal for additive manufacturing, which industrial applications are rapidly expanding. There are many advantages, such as its freedom to design, flexibility. Basically, the additive manufacturing paradigm in general is evolving and becoming a robust manufacturing paradigm. On the other hand, injection molding is possibly the most widely adopted manufacturing technique to produce large series. The process is very time efficient. This is partly explained by the fact that conventional molds produced in specialized tool steel or aluminum maintain their properties over a large number of produced parts. Furthermore, due to the mechanical resilience of these molds, high pressures, temperatures, and injection speeds can be used, speeding up the process and making it so prominent. However, in the context of flexible mass customization, where often small series production is envisaged, both the typical lead times and the costs associated with producing a tool steel mold hampers the economic viability of injection molding. In this context, the application of additive manufacturing for the production of plastic molds inserts for injection molding can prove to be a cost-efficient alternative. However, to integrate such additive manufacturing inserts into the injection molding process, their mechanical reliability with respect to the thermo-mechanical loading has to be fully understood to ensure final part quality, process reliability, and minimize the number of service intervals. To give a brief impression, you note the difference in Young's modulus of polymers and alloys on this logarithmic scale, which clearly indicates that the range of materials that are applicable for most additive manufacturing methods, although quickly expanding, is not on par with conventional methods for injection molding tools. Before continuing, let me give a brief overview of how this presentation is organized. I've given a general overview to situate this work, where we also saw the problem. So we will now have a look at two tests to assess thermal properties. Next, we will have a look at a case study, which I will use graphically to explain together with you the proposed methodology. More details on that later. And finally, the conclusions. First of all, material tests. Why did we do this? Several thermo-mechanical material parameters that have a large impact on the quality of an injection molding mold produced in digital ABS, and hence the performance of the injection molding process, are insufficiently quantified. The rather high thermal expansion coefficient, the low thermal conductivity, and the low glass transition temperature of the digital ABS cause risks of premature failure due to the thermal load induced by the injected polymer melt. Therefore, establishing these parameters is a fundamental prerequisite to obtain a robust production process, as well as developing truthful numerical models. Differential scanning calorimetry (DSC) analysis is used to assess the thermal capacity and an interval for the heat deflection temperature within the range of 0 to 200 degrees Celsius. Thermo-mechanical analysis (TMA) is used to determine the thermal expansion. More info regarding these tests are written in the paper. In previous work, we already hypothesized that the shear rates induced by the plastic melt that is being injected are the key factor determining the failure of the plastic additive manufactured insert. This hypothesis was based on the observation that the mold consistently failed at locations where the highest shear rate occurred during the injection molding process. Furthermore, it is expected that the lack of thermal conductivity of the material causes large temperature variations within the mold during each shot, inducing large inducing thermal stresses in the material. These effects, in combination with a relatively low yield strength of typically used materials, can cause failure of the insert after a low number of cycles, mostly less than 100. Nonetheless, these effects should be fully understood to ensure the reliability of the mold inserts. This paper therefore studies the dependence of shear stresses and temperatures during the injection molding process on the functional life of the mold. Here I've illustrated the design of our case. As you can see on the right, we use a base mold and we only print the insert, which is illustrated on the left. By doing this, we save a lot of material, but we are restricted to the available space in the inserts. Let us take a closer look at the selection of this case. It results in a design consisting of 4 cavities with the same volume, but with different injection gate widths, ranging from 1 mm to 4 mm. To ensure an equal thermal stress during injection, the model is kept as symmetric as possible. The optimal cavity size and corresponding gate positions, as well as the optimal injection parameters, are found by means of numerical optimization based on a finite element model. The illustration on this slide stems from that model, indicating the maximal shear rate, which we can clearly see is increasing in proportion to the gate size. In the design optimization, the cost function represents the difference in fill time, which is minimized. As such, the thermal loading of the mold material in each cavity should be equal, as the same heat exposure time is ensured. Note that the latter does not include the incoming flow. Also note that the sprue is still steel, and thus there is a large transition in thermal behavior where the flow enters the inserts. On this slide, we can track the temperatures on the wall during injection. Let's try to pay attention to the absolute time during this video. The period where the flow enters is stretched quite long, and cooling will play fast. This is the moment where you can clearly see the high occurring temperatures inside the mold. The injection molding parameters, such as cooling between shots, injection pressure, temperatures, and hold pressure, that have to be used in combination with plastic molds, differ significantly from conventional injection molding due to the vast difference in properties. This is illustrated by choosing one variable, thermal conductivity. Phi, the heat flux, is equal to the coefficient of thermal conductivity, in this case either 30 or 0.20, multiplied by the area of contact and the difference in temperature. The heat flux, upper temperature, and area of contact are assumed constant, so the difference in coefficient will make the temperature through the wall much higher. This will cause the frozen layer to grow slower, making it possible to inject at lower flow rate, which will result in lower shear forces. The point here is that the process parameter differs substantially from conventional injection molding. The illustration provides some information on the optimization process. The goal is to lower the injection pressure, and thus shear rates correlate to the latter. The process also has a boundary condition that the cavity should be completely filled, temperatures should be within the range of the material, and gradients of sudden velocity, etc. should remain feasible for the selected machine. The hypothesis that shear stresses and thermal loads are responsible for premature mold failure is validated according to a well-monitored experimental campaign, based on the optimized design. Specifically, it is expected that in case first failure of the molds occurs in the 1 mm gate, shear rates are the predominant factor, since the highest shear rates occurs at that place during the injection molding. The experimental campaign is both aimed at validating the proposed parameters as well as assessing the functional lifetime of the mold. The state of the mold and the temperatures are closely monitored between the consecutive shots. Due to the previous elaborated material tests, we were able to construct a model that is able to predict the temperatures quite well, which can be seen by the comparison of the thermal distribution in both the experiment and the finite element model. After the benchmark of 100 shots, the mold degradation is already noticeable. The occurred failures of the mold insert are summarized on the illustration on the bottom, which illustrates the location of the fractures, also written down in the table, which gives the corresponding shot numbers. Reviewing the occurring damage to the mold material reveals that damage is not correlated to the size of the predefined sections with high shear rates. In fact, opposed to what was hypothesized, the 1 mm gate did not fail within the 100 performed shots. Actually, the occurring high temperature concentrations are the main cause of the early failure in the mold in these gates, which is most probably due to a combination of thermal expansion and degradation of the digital ABS material. Finally, our conclusions of this work. Injection molding with additive manufactured plastic molds has a large potential in the context of flexible mass customization, as it can combine the strengths of the conventional injection molding in terms of production throughput with the flexibility of additive manufacturing techniques. Most commonly, plastic inserts for steel molds are produced, yielding hybrid molds. However, the thermo-mechanical behavior and the functional lifetime of these mold inserts is insufficiently understood in literature to allow for full industrial uptake. Mostly, their robustness with respect to the occurring shear rates and thermal loads remains an open question. Therefore, in this paper, a case study is defined and optimized to have predefined occurring shear loadings at different sections in the mold insert. This case study consists of a design with 4 cavities with varying widths of the gates in combination with numerically optimized injection molding process parameters. An experimental test campaign consisting of 100 shots in combination with this design reveals that in fact temperature concentrations are the main cause of failure, possibly combined with high local stress concentrations inside the mold due to large temperature variations. Using numerically optimized parameters as a prior setting, the lifetime of the mold in digital ABS was higher than predicted. Yet, the parameters required small adjustments during the experiments to achieve the final product. Finally, to attract people to read the full paper, we also demonstrate a scanning electron microscope analysis on the produced parts to verify the hypothesis on the absence of a frozen layer in parts produced with plastic inserts. The results in this paper may serve as a basis to further optimize the designs of plastic inserts for injection molding and the parameters used to produce parts with these inserts. It furthermore highlights that numerical models of the process can aid in the design of these inserts as well as the optimizations of the injection molding process. Thank you for listening.